Hey everyone, today we're going to be talking about charge density. So, in previous videos, we've been talking about point charges. So let's draw a charge, and we're going to call this Q. For all intents and purposes, when we do calculations with Coulomb's law, we say that this charge is a point charge, which means there is a point at the very middle, and that's where we consider that charge to be. It doesn't take up any space at all. It's just at that very, very small point. In reality, when we're using electric charges, we actually disperse charges along wires, along plates, and even volumes. And we have to define those differently in order to get accurate representations of how much charge an object can hold. So let's draw these out. So there's a point charge that we've gone over. Then there's a charge along a line, which is generally a wire. So I've drawn this wire a little larger so you can see it, but for all intents and purposes, it's just a straight line. It doesn't have any area or volume, just a line. Okay, so there's the wire, a plate, which is a plane, and it has an area associated with it. This only has a length associated with it. And then a volume. So the area actually has two lengths associated with it, and volume has 3. We use 3 different variables to describe the charge density of these objects. So for the wire, we use lambda. For the plate, we use sigma. And for the volume, we use rho. Let's talk about how these are defined on the next page. So let's start with the simplest case, a wire. So we said the wire is defined by lambda. So we want lambda to be a consistent variable that can describe how much charge is on this wire for any length of it. So lambda is going to have the units of charge, which is coulombs, per meter, right? So charge per length is what that is. So if I were to say that you had a wire that was 2 meters long, and I told you that I put a charge of 4 coulombs onto the wire. And what do we know about conducting wires? The 4 coulombs is going to spread out because the charge wants to be as far away as it can. So it's going to move throughout the wire and spread out as much as it can. So lambda, in this case, would be the charge, 4 coulombs, per length. So it's spread along 2 meters. And when you do the math, you get 2 coulombs per meter. So for any portion of this wire, lambda is going to describe how much charge is there. If, say, I wanted to know how much this 0.25 meters, how much charge was on that 0.25 meters, I could say 0.25 times lambda is going to equal the charge, right? So that's this equation. Lambda equals charge over length. So length times lambda gives you your charge. Okay. So there would be the same thing even if you were given a curvy wire, if you were to know the length, or actually let's go the other way. Say you were given lambda. Say you were given lambda equals 6 coulombs per meter. And then you were told that this wire of whatever length has Q equal to 3 coulombs on it. So we can actually figure out the length of this wire with these variables. So rearranging the equation, you get L equals Q over lambda. So that's just rearranging this, right? So the length here is simply going to be 3 divided by 6. The units are going to cancel, a meter is going to come up top, and it's actually going to be equal to 1/2 of a meter long. Okay, let's talk about a plate. So, a plate is described by rho. Sorry, sigma. The units of sigma are going to be coulombs per meter squared. So notice how the wire was just per meter because it only had a unit of length. A plate has an area, which is meters squared. So the formula that we have is sigma equals charge divided by area. So, say I gave you a square plate of 1 meter on each side, and a charge was dispersed on the plate equal to 4 coulombs again. To figure out sigma, you would simply take 4 coulombs and divide it by the area, which is length times width, which would simply be 1 meter squared. So your answer would be 4 coulombs per meter squared. So if I were to be asked how much charge is on this fourth of the plate, you could figure out the total charge on the plate and divide by 4, or you could simply figure out the area of the blue spot and multiply that by sigma. So we'd rearrange this equation. The area times sigma equals the charge on that portion of the plate. Okay, lastly, let's talk about volume. So volume, there are 3 dimensions, 3 lengths, right? So volume is described by the variable rho. And this equals the charge per volume. So it's coulombs, charge per volume, and that is equal to coulombs per meter cubed. Okay, so in this case, you do the same thing as the plate and the wire, except instead of using a length or an area, you use your volume. So let's say all of the L's, right? So we have a box, and every L equals 2 meters. So the volume equals 2 meters times 2 meters times 2 meters, right? Equals 8 meters cubed. 8 cubic meters is our box. Pretty big box. And we distribute a charge equal to 16 coulombs throughout the volume. So the charge density of that volume is going to equal 16 coulombs across the box divided by the volume in meters cubed. So the charge density that describes that box will be 2 coulombs per meter cubed. So if you were asked, well, how much charge is in 1 cubic meter of that box? You would rearrange this equation and say the volume that you were given, so in this case 1 cubic meter, times rho, which you found here, equals the charge in 1 cubic meter.